So recall in last class we discussed about modified Dirichlet function. The idea is that it is 0 at an irrational number, so r minus q intersection 0, 1. The reason is we are defining this function from 0, 1 to r, so we are only defining this on an open interval 0, 1. And it is 0 if x is irrational, and if x is a rational number, then every rational number can be written in form of m by n, right? Where they are in the lowest term, that means the GCD of m and n is 1. And in that case, we define what f of x to be 1 over n. All right. Now, one thing one should also look at is that this function meaningful, right? That means is it well defined, and that you can prove easily that it's well defined. Okay. By taking that, let's take two representative of rational numbers and or by arguing that a representative of rational number in a lowest term is unique. Okay, so either one of them should help you to make sure that this function is well defined. Now let's try to prove that this function is discontinuous at every rational point inside 0, 1, and it is continuous at every irrational point inside 0, 1. So let's start with the first one. So let's say let a belonging to 0, 1 be rational. Yeah. So construct a sequence of rational number, sequence of irrational number, converging to A. Yeah, this can always be constructed because of the density of uh, of of rationals in R. All right. So it would be an interesting construction, right? So please try to construct one. It would basically amount to taking an 1 by k neighborhood of A, and then you start making k smaller and smaller and pick up element from each of those 1 by k neighborhoods. Okay. So now we have sequence of irrational numbers, say xn. Now xn converges to A, right? But what about f of xn? F of xn is constant 0 for all n because xn is irrational. But what about f of a? So f of a is, but f of a is not 0, right? Why is that? Because a is what is irrational in 0, 1. This implies what a equals to alpha by beta, where beta belongs to z and beta is not 0, right? So therefore we get what? So f of a is going to be beta, all right? Where alpha beta, the GCD is 1, right? So therefore we get what? We get xn converging to A, but f of xn does not converge to f of A. Yeah. So therefore, what? F is not continuous at A. All right. So recall what was the definition of continuity? The sequential continuity definition was the following. For any sequence, so f from D to R is continuous, is continuous at A if for any sequence xn in D with xn converging to A, then f of xn converges to f of A. Okay, this was the definition. This was the sequential continuity, right? So now the second part is to show that let C belong to let's write it proper. So let's C be a irrational number in 0, 1. Claim that f is continuous at C. Okay, so let's prove this now. So what is the idea behind it? The idea is the following. Let's take xn be any sequence which converges to C. Yeah. So if xn belongs to, if xn is a sequence in r minus q, that means if xn is irrational, then f of xn is going to be 0. So that's not a problem. However, if xn is rational, then you can choose the ones which denominator so small that f of xn will be basically less than equal to some fixed k. All right, and this k can be made less than epsilon by the starting point of the continuity, right? So this is the idea behind it. So let's proceed with that. So how do you show that f is continuous at C? Now, so now can you hear the? So now there's okay, yeah, but it's not continuing, right? It just once. Okay, all right, okay. Well, we'll fix that for the next time, right? So okay. So now next claim is that f is continuous at C. So first of all, f of C is 0. So what do we want to show that it's continuous at C? So given, so that is to show given epsilon greater than 0, there exists,
My room is so messy.
given epsilon greater than 0, there exists delta greater than 0 such that what mod of x minus c less than delta implies f of x minus f of c is less than epsilon. Okay, so this is what I want to show the continuity at C. All right. So now f of c is 0, right? So that is, I want to show that if x minus c less than delta, this implies f of x minus 0, because this is 0, right, is less than epsilon. And f of x is always positive, so we need to show that this is less than epsilon. Okay, so how do we go about it? So what do we want is that whatever the output of f of x is, it's going to be less than epsilon, right? So we want to control the output of f of x in a way that it's always less than epsilon. So we'll appeal to the Archimedean property and make sure that f of x output does not exceed certain k. Okay, so let's say, so given epsilon greater than 0, there exists k belonging to n such that 1 by k is less than epsilon. And whenever you're using some property, you have to basically, you have to write it down. What property, by what property can you basically say this is true? Now let's consider C here. Now let's ask the following question. So how many of, so what we want is that we want that f of x, output of f of x should be basically less than or equal to 1 by k. This is what we want, right? So what we really want is that if f of x is, if f of x was, if x is irrational, then we are okay, as we saw here. If x is irrational, then the output is 0. However, if x is rational, then what we want is, suppose it's a rational of form m by n, then we want that this has to be less than equal to 1 by k, right? This is what we want. Yeah. So the idea is you take C you construct a neighborhood around C in which there are terms, the only terms which are having the denominator less than equal to n are really small, or less than equal to k are very small, right? So we can basically construct, so let's try to finish this proof now. So f of x is less than equal to k. So claim one, there are finitely many rationals in 0, 1, not throughout the whole real numbers, but in 0, 1, such that denominator of x is less than equal or less than k. Well, equal to is fine because we have less than k, right? Do you buy that? Well, think about it in the following way. Suppose I have 1 by, so I want denominator to be what? There are finitely many with denominator less than equal to k. So suppose I have k minus 1. Now, how many options are there for on top? So let's take a upon k minus 1, where your a is natural number. Now, how many of them are there so that uh, this number will still lie in 0, 1? So of course, clearly, k has to be what, a has to be greater than equal to 1 and less than equal to k minus 1. Actually, it has to be less than equal to k minus 1. So you see how many possibilities are there. There exactly utmost number of possibilities is k minus 2 possibilities, right? In fact, if to be more to be precise, if you are interested, number theoretically, there are phi of k minus 1 possibilities such that this is a legit number. So now for k minus 1, you have k minus 2, right? So you go all the way until what? Until 2, and these are all the possibilities, right? So there's nothing beyond that, and whatever k is, say k is 1 million, still this collection of numbers is finite. Yeah. So the claim that there are finitely many rationals in 0, 1 such that denominator of x is less than k, right? So what you do is, therefore we can construct, therefore take C, find delta greater than 0 such that what, C minus delta and C plus delta. So if you look at C minus delta and C plus delta, such that for this interval, all x belonging to C minus delta and C plus delta with with x as rational can have what? Have denominator greater than or equal to k, right? And that can be arranged, right? Because these are finitely many. You have C, and then you have finitely many numbers. So you choose the distance. You can choose the distance between them, all of them, choose the smallest distance between C and these numbers and call that as delta. So none of them will be in neighborhood less than in the neighborhood of C of length less than delta. Okay. So therefore we have the following. So this would imply that moment you have x minus C less than delta, this would imply f of x, the denominator of this is going to be what? 1 by m, and that is going to be less than equal to 1 by k, and this is less than epsilon. So you have proved that f is continuous on any irrational 0, 1. So there are few things here, few caveats here which were not proved, which are not written properly. Perhaps one is to construct the sequence of irrational converging to A. Yeah. So you could be tested on such caveats, right? That how do you construct a sequence of irrational converging to A, right? And things like that, so on and so forth. Okay, so this is an example of a very interesting function which is continuous at irrationals in 0, 1 and discontinuous at every rational. Now note that you can have a variation of this and extend this to whole of R. Yeah. So it will be an interesting exercise for fun. Construct f from R to R, continuous on R minus Q and discontinuous on Q. Okay. And then another interesting question is 2, is there a function f from R to R which is continuous on R minus Q, sorry, continuous on Q, but discontinuous on R minus Q. Okay, so both of these problems are interesting. Well, the first one is just taking the previous problem and applying the translation to cover, say using this property from 0, 1, you can cover 0, 2, sorry, 1, 2, or and so on and so forth. Okay, so or using 0, 1, you can cover 0, infinity. All right, so think about that. Okay, so let's move on to the next part. So oops, sorry. Okay, seems like I have to draw usually like that. All right. Okay. So now there is we'll discuss the algebra of continuous function, namely the following theorem. So let f and g be continuous from D to R, and let C belong to D. Hold on, I shouldn't write this f and g is continuous from D to R. However, we'll have the extension of definition. The idea is that a function is continuous on its domain if it is continuous at every point inside. And by that, we mean at the endpoints. If it is a closed interval at the endpoint, it should be left or right continuous based on where they lie. Okay, so we'll come to that. So let f and g be functions from D to R, and let C belong to D. Then, and on top of that, let f and g be continuous at C. Then clearly the following holds: 1, f plus g, f times g are continuous at C, and b, f over g is continuous at C if g of C is non-zero. Right? So I will basically prove the first one. So proof. Also, another thing is let alpha belong to R and alpha belong to R. Then clearly C alpha f is continuous at C as well. Okay. In fact, you can go further. You can basically construct, if you take a function, all the continuous functions from D to R, you can basically give it a structure of basically some kind of a structure of vector space. And if it doesn't become zero, then you can give it a fact. You can try to give it some kind of a structure of field as well. Okay, but for now, we are only interested in these statements. So let's prove one of these. So I'll go with the first one. The proof is also in the textbook. You could be asked one of these in the exam for that matter. All right, because the proof is not given to you. So okay, so let's say we'll use sequential criteria here. So let xn converge to C. Now xn is any arbitrary sequence, all right? So what do you want to prove? To show that f plus g of xn converges to f plus g of C, right? So this is what it means by, so we start with any sequence xn converging to C. To show that f plus g is continuous, you have to show that f plus g of xn converges to f plus g of C. So first of all, what is the definition of f plus g of xn? F plus g of xn by definition is f of xn plus g of xn. All right, this is what it means by f plus g of xn. Now, so therefore, limit of f plus g of xn is basically going to be limit of f of xn plus g of xn, right? But now limit properties are as follows. If you have Sn and Tn, then limit of Sn plus Tn is limit Sn plus limit Tn. So this is going to be limit of f of xn plus limit as g of. But note that these functions f and g are continuous at C. So therefore, this is going to be f of C, and this guy is going to be g of C. And they can be written as f plus g of C. This is what the definition is. By f plus g of C is same as f of C plus g of C. So therefore what we have shown that f plus g is continuous. Okay. So similarly, you can prove the other properties as well. Okay. So now another interesting fact is the following. So theorem. And this is going to be useful later on as well. So max of fg is also, so let's do this continuation of this theorem. So f and g are continuous. Let's say continuation of above theorem. Max of f plus g, f comma g is actually half f plus g minus, sorry, plus half absolute value of f minus g, and min of f comma g, which is half f plus g plus, sorry, this is minus half f minus g, is also continuous. At what? At C. Okay. So now the proof of this is interesting. Proof. So here, what you have to do is first you need to prove that f minus g is continuous at C whenever f and g are continuous at C. Okay. Note that this is true, right? I mean, like if you take max of two numbers, So max of two numbers alpha and beta. So max of two numbers alpha and beta is going to be half alpha plus beta minus half alpha, plus absolute value of alpha minus beta. Yeah. I mean, how do you argue this? You can argue this by taking two cases. If this is alpha, if this is equal to alpha, then this is going to be what? Half alpha plus beta as usual, plus half. Again, then alpha is bigger than beta, so absolute value of that is just going to be minus alpha plus beta, right? And then when you add this up, beta disappears. You have 2 alpha by 2, which is going to be alpha. Similarly, if this was beta, then things would be exactly symmetric, and you will have beta minus alpha, and the alpha would disappear and you'll get beta. So similarly, you can show for the minimum as well that minimum of f comma g is half f plus g minus half of absolute value of f minus g. Okay. So to prove this, all you have to do is first you have to show that this is continuous at C, all right, and then 1. So how would you show that this is continuous at C? So start with the following. Start with, if f is continuous at C, then absolute value of f is continuous at C, right? So if you can show that you already have f minus g is continuous, therefore absolute value of that is continuous, combine that with algebra, and that's how you'll prove the whole thing. So let's take questions for the moment. So now the next part is the following. So suppose you have, let's talk about composition of two functions. So consider a function f. So we want composition of functions. So let's take function f from D to another set E. Let's call this function as f. And let's take another function from, so this function is f. Let's take another function to R. Let this function be E. Okay. So we have function from, so let this be C, you go to f of C here, and then you apply g to this function and you reach to point g of f of C. So g of f of C. Make it bigger a bit. G of f of C. So the statement is the following. So suppose you have a function, continuous function f from D to R, some domain D. You have function from E to R, and what you need is that the whole of this D at least goes inside this function, right? We need that f of D as an image sits inside E. Then the claim is that you can talk about function g of f going from D all the way to R. So consider this function. Now, suppose f is continuous at C. So at C, your f is continuous. Then by f, you're pushing it to f of C. And then what do you have is that G is continuous at f of C. Then what? Then G of f is continuous at C. Sorry, yeah, that's right. So G of f is continuous at C. Now the proof of this is not hard. Proof, you can use any proof really. I mean, you can either use epsilon delta proof, or you can basically use sequential continuity, or you can use the neighborhood concepts. Any one of them will work. So let me give you that as a homework. right? Okay, so that is the so this is about the composition of two functions being continuous. Now comes the next one, theorem. All right, sorry. Sorry about that. So if arbitrary union of open set is open, this would imply what? H is open. All right. Now H is open, and what is H intersection D? Now H intersection D is F inverse of G. Yeah, that will require some proof, but it's not difficult. So requires proof. Okay. So this is a setup. So conversely, you have to show the following. Conversely, what do you have to show? Conversely, that if inverse image of every open set is open, then F is continuous, right? So conversely, so let's say let C belong to D and V be open neighborhood of F of C. Now to show that F is continuous for neighborhood of F of C, I should be constructing a neighborhood of C with certain properties, right? So since V is open, this implies by our criteria there exists H, a neighborhood of we need to show that it's a neighborhood of C, but there exists an H. Our statement says that there exists an open set H in R such that H intersection D is F inverse of G, right? So we can say that there exists H, open neighborhood in R such that H intersection D equals to F inverse of B. Now what we still want to show that F is continuous. Now note the following: F of C is an element of V. So therefore, what do we have? We have C belongs to H, right? But H is open. This would imply that there exists a neighborhood U of C such that U is subset of H, right? That's a property of the open set, that if you take any point inside, you can get a neighborhood which will also be inside H. So this would mean what? This means F of U intersection D. We want to show that this is subset of V. This is going to be F of H intersection D because U is a subset of. Therefore, we have proved F is continuous at C, but since C belongs to D is arbitrary, F is continuous at continuous on D. All right, so